Okay, so let's see chapter 35, AC circuits. So alternating current circuits are just like our regular DC circuits. DC, of course, is direct current. So we can say in the AC circuit, we have an alternating source. And we can say the source EMF is of the form, and we can say E of T equals E naught cosine omega T. So it's an oscillating circuit or oscillating EMF, where the angular frequency omega is equal to 2 pi f. We can start by looking at an RC, a resistor circuit. So let's look at the resistor circuit first. So I'll start off by drawing the circuit. So this is the symbol for an alternating source, and then we have our resistor like that, and this is the resistance R. So we have a current I going through it, and this is the EMF E. So E is just the same as the potential difference of the source. So by our loop rule, we use our loop rule, we just write that the potential difference of the source plus the potential difference of the resistor should be equal to 0. And so we know that the potential of the source, or the EMF, minus IR is equal to 0. Remember the loop rule, when we are going across the resistance, we make it minus or negative, so minus IR. So the voltage across the resistor, so we can say E is equal to IR. Therefore, the voltage across the resistor can be written as a certain voltage V. Let's put V naught cosine omega T. Your book uses VR in both cases, but they use a lowercase v on the outside. I can't simulate a lowercase v, so I'll just use V naught for the peak voltage. So VR equals V naught cosine omega T. So by Ohm's law, we have that the current IR is equal to VR over the resistance. So we can say this is equal to V naught cosine omega T over R. So we can write this as I naught cosine omega T, where we are saying that I naught is just equal to V naught over R. Okay, so that's the peak current I naught. I naught is equal to V naught over R. So we can draw a diagram, or at least we can plot a graph of how this looks like. Okay, so if I plot the graph this way, let's do this like that. So this is T, and you can see that this is a cosine graph, so the EMF is a cosine, of course, so we can go like that. And this is a bit longer than I want, so let me delete a little bit, something like that. So this is the cosine graph. And then for the current, so this is the V naught over here, and then for current we can start like that and go this way. So this is I naught. So this is for VR, IR. So this is how the current and the voltage will look like. This tells us that the current and the voltage are in phase. So we can say that for our resistor circuit, the current and voltage are in phase. So let's say current through the resistor is in phase with the voltage. So the current and voltage are in phase for a resistor circuit like this. We can represent this also on a phasor diagram. So we can say it is convenient to represent the voltage and current on a phasor diagram. So we can look at what a phasor diagram looks like. A phasor is just a vector representation. Okay, so we can say a phasor is a vector that rotates counterclockwise. And so in our case, it rotates with angular frequency omega. So if I draw the phasor diagram this way, we can say the phasor is this way. So this is the voltage in the resistor, and the current in the resistor is IR. and it's rotating with angular frequency omega, and so the angle is omega t. So we can say it rotates like that. So the peak is V naught, and the peak is I naught. Any questions on phasors at this point? So we can go on to the next thing. Let's see. Okay, let's go to the next section, which is 35.2 capacitor circuits. Let me do it on a different page. Maybe before we do that, we should do a quick example. Sorry, let's do a quick example. So let me delete this section, what I've put here, so we can do the example first. I was thinking to do it at the end, but I want to separate the example. So let's do the example here. So for this circuit, we can do this. So this example is from your textbook. This is example 35.1. So the question is to find the peak voltage across each resistor and the instantaneous resistor voltage at t equals 20 milliseconds. So the first thing we need to do is to find the equivalent resistance of the circuit. So let's do the solutions down here. So A. So first find the equivalent resistance of the circuit. So what is equivalent resistance? So this will be R equivalent. So R equivalent is just equal to R1 plus R2. And we have our E. So just like we did for DC circuits, remember this is just like what we did for DC circuits. This is a current going through the circuit I. So we can say that by Ohm's law, the current I is equal to V through the resistor divided by the equivalent resistance. Okay, so we're just using Ohm's law as usual, where this V is just equal to V naught cosine omega t divided by R equivalent. So that's what we did earlier. So this is the current that will be going through the equivalent resistance. So we already know that V naught is 100, and we know R equivalent, so we can find I naught, peak current. So I naught is equal to what? V naught over R equivalent. So we have V naught, which is 100 volts. R equivalent is what? 20 ohms. So what is I naught? 5 amperes. So the peak current is 5 amperes. So we are saying that I is equal to 5 cosine omega t. That's how you write it, because the peak is 5. So now that we know what it is, we can find the potential drop across each of the resistors in the circuit. So it says find the peak voltage across each resistor in the circuit. So we have the peak current. So that peak current is going through each resistor in the circuit. So let's draw it this way. So this is our circuit again. So now we are working our way backwards the way we did for the DC circuit. Okay, so we know the current is now I naught, which is 5 amperes. And we know this is E of t, of course. So what is the peak voltage across each of these resistors? What is the voltage across a 5 ohm resistor, the peak voltage? Just from Ohm's law. No, that's the resistance. What is the peak voltage? Yes, 25. So it's just going to be the peak current times the peak times the resistance. So this is equal to 5 amperes times 5 ohms. So this is 25 volts. So that's the peak voltage across the first resistor. What is the peak voltage across the second one? Yeah. So this is 5 amperes times 15. So this is 75 volts. So these are the peak voltages across each of those resistors. Okay, so that's part A. So part B says that what is the instantaneous current at t equals 20 milliseconds. So part B, instantaneous current. Instantaneous current at t equals 20 milliseconds. So what is the current formula? Current is equal to V over I. There is V, no, there's a formula for current there already. So current I, let me remind you that this is a current which is a function of time, and it's equal to 5 omega t. Okay, we already know what omega is. What is omega? 2 pi f, and f is equal to 60 hertz. Okay, so remember we wrote that all up here. Sorry, I wrote omega is 60 hertz. It's not omega, it's f. So f is 60 hertz. Okay, so make that change in what I wrote earlier. F is 60 hertz, not omega. So we have omega equals 2 pi f, and f is 60 hertz. All right, so let's now calculate the current at 20 milliseconds and tell me what you have. That's the instantaneous current. So all you have to do is I at 20 milliseconds is equal to what? Okay, so I at 20 milliseconds, okay, so 1.55 amperes. Okay, thank you. So now we can calculate the potential drop, instantaneous potential drop across each resistor in the circuit. So now we have I of T. So this is 5 ohms again. This is 15 ohms. So what is the instantaneous drop across resistor 1 and instantaneous drop across resistor 2? So just like we did before, again, we are still using the same Ohm's law, V equals IR. So what is the drop across the 5 ohm resistor?
7.75. Yeah.
Okay, so it's going to be the instantaneous current multiplied by the resistor. So it's going to be 1.55 multiplied by 5 ohms. So you said 7.1? 7.5 volts. And then the same thing applies here. This is R1, R2. So it's going to be 1.55 multiplied by 15 ohms. So what would that be? 23.25 volts. So we've calculated the peak voltages across each resistor and the instantaneous voltage at a given time across each resistor. Okay, so that is how you use this kind of AC circuit to do a calculation. Questions on this? Okay, so let's go to the next section, which is 35.2. I'll put it on a new, different page. So 35.2 is capacitor circuits. So the only thing we're going to do now is to introduce a capacitor into the circuit. So let's consider AC source with a capacitor of capacitance C. So we have our source again, and this time we just have a capacitor connected in it. So this is the EMF again, and this is equal to the potential difference of the source. And then for the capacitor, so that's the voltage across the capacitor. Therefore, the charge is going to be equal to the capacitance times the voltage across the capacitor, like that. And so with that in mind, we have here also that so Q is equal to C times voltage across the capacitor, where the voltage across the capacitor is just equal to the EMF, which is equal to V cosine omega t. Okay, so this is just going to be like that. So this will be our V naught. So we can say the charge Q is equal to C V naught cosine omega t. And I'm using V naught because there's uppercase and lowercase v, and I can't really simulate that. So I'm just going to use this approach of V naught instead of V. Let me make the C bigger. So this is the capacitor, like that. So the current flowing through this circuit can be found by taking the derivative of the charge. So this is I. Okay, so the current through the circuit, the Q dt, is equal to I, and which is equal to C V naught, and then which has U d dt of cosine omega t, like that. Okay, so the current I, remember this is a current which is a function of time, I of t can then be equal to the derivative of cosine is negative sign, so minus C V naught omega sine omega t. And then so we have I of t equals minus C V naught omega sine omega t. We can use a trigonometric identity to write this in a form using cosine. So let's say we'll write this with cosine instead of sine. Okay, so the identity that will work is to know that minus sine omega t is equal to cosine omega t plus pi over 2. So we'll replace minus sine omega t by cosine omega t plus pi over 2. Therefore, we can say that I of t is equal to C V naught omega cosine omega t plus pi over. So what this can be interpreted to mean is that the current through the capacitor leads the voltage across the capacitor by a phase difference of 90 degrees or by pi over 2. So what I've shown you here, we know the voltage across the capacitor is the same as the EMF. So that will just be V naught cosine omega t. But the current across the capacitor is given by this quantity. So let's write it down. So voltage across capacitor is V capacitor, which is equal to V naught cosine omega t, and current through the capacitor is I of t, which is equal to C V naught omega cosine omega t plus pi over 2. Okay, so this is just telling us that the capacitor voltage is ahead of the the capacitor current is ahead of the voltage across the capacitor. We can plot that this way. So we know that the voltage is like that. Okay, so this is V naught. And then we can look at the capacitor. So the capacitor is 90 degrees ahead. So we'll start off this way. Let's see if I can make it work. Something like that. So this is the current through the capacitor. So you can see that this is shifted by 90 degrees. And then let's write this in phasor form. So if we write it as a phasor, we have here, this is going to be the voltage across the capacitor. And this is omega t. And so the current through the capacitor is this way. Let's see if I can do a better job with that. Something like that. So this angle here is 90 degrees, of course. So this is going to be omega plus pi over 2. Omega t plus pi over 2. That gives you the entire angle there. Omega t plus pi over 2. So this is the current through the capacitor. So notice the difference between what we had with this. So this is capacitor circuit. This is the phasor for a capacitor circuit. And let's compare that to the phasor diagram for a resistor circuit, where the voltage across the resistor is this voltage here, and the current is the same, I. Okay, so they are in phase. So you can see the difference there. So what we can do now is now look at Ohm's law. So we see that this is current, and we can now apply Ohm's law now. So let's now compare to Ohm's law, V equals IR. So in this case, the peak current I naught in the capacitor is given by I naught equals omega C and V naught. Okay, so that's the peak current. So if we write the current through the capacitor I of t, we can write I naught cosine omega t plus pi over 2. Okay, where I naught is just omega c V naught. So that's the peak current. So this just tells us that if we compare this to Ohm's law, then we can say V naught is equal to I naught over omega c, where the equivalent quantity for resistance in this circuit is equal to 1 over omega c. This is called the capacitive reactance, X subscript C. So we can say that X subscript C is equal to 1 over omega c for a capacitor circuit. So if you like, we can put this together and say Ohm's law for this circuit is V naught equals I naught XC. XC has a value of ohms, so XC is just equivalent to resistance, and so it has a value of ohms. Okay, so this is for a capacitive circuit. XC is a capacitive reactance of the circuit. We can do a quick example on that. Okay, so let's do this example. This is example 35.3 in your textbook. So let me draw a picture of the circuit for you. So we have the EMF, of course, and then we have our capacitor this way. So this circuit is the same as what we have or what we drew earlier. This is E, and this is the current I going through the circuit. So E is equal to E naught cosine omega t. So you know what omega means, right? The angular frequency omega, we know what that means. We have formulas for peak current. Peak current is equal to omega c times V naught. We have XC, which is 1 over omega c. So we have all this information. So the question is, what is the peak current in this of the capacitor? Okay, let's look at the solutions. What do you have for the current?
I'm pretty sure mine's wrong. I got 0.3142.
Okay, let's see. So peak current.
0.125.
What do you have?
0.1256.
Okay, you got 0.31 and then 0.125. So let's write both of them. So what we had is, remember that we had a peak current equal to the voltage over the resistance. And in this case, the voltage is just the peak voltage across the capacitor, and the resistance is the capacitive reactance XC. So XC is equal to 1 over omega C. Okay, we already know the peak voltage. Let's see. The peak voltage is 5 volts, so we already know that. So we need to find XC. So XC can be found by taking 1 over omega, which is 2 pi F times C, and F is equal to 1 kilohertz or 1,000 hertz. C is equal to 10 microfarads, I believe. That's what we had. Yeah, so that's 10 times 10 to negative 6 farads. So you can calculate the capacitive reactance. What do you get for that? And then I'll put times 10 to the power 6 on top. I've just transferred the negative 6 at the bottom to make it 6 on top.
15.92.
And what is the unit? Ohms. Capacitive reactance is in ohms. So the current can be found by taking the peak voltage divided by 15.92, and that gives you what? That should be about 0.31.
Wow, I did it a completely different way.
Oh, okay.
Weird, but I got that 0.31.
Okay. Yeah, 0.31. All right, so that's how you use this kind of formula. Okay, so you have to make distinctions between the peak quantities and the variable quantities. So we have peak current, we have peak voltage, we have variable current, we have variable voltage. So make sure you make that distinction. Let's go to the next item there, which is the RC filter circuit. So I'll do that on a different page. So this is 35.3. So we'll take advantage of what we know of the resistor circuit and the capacitor circuit to build our RC circuit. So we shall consider the circuit with both a resistor and a capacitor below. So we have our source, which is alternating, and then we shall have our resistor like that, then the capacitor. We've put them in series, that's okay. And we shall have a current I flowing through. So this is R, and let's say this is Q over C, and this is our EMF, of course. So we know that the EMF, of course, the EMF is equal to E naught cosine omega t. And so we know what the voltage across the resistor and what the voltage across the capacitor is, because we've already seen that. So we have already seen the results for the resistor circuit and the capacitor circuit. We shall use those results. So let me just remind you. So for the resistor circuit, the voltage across the resistor is equal to V naught cosine omega t. Okay, and then for the capacitor, the voltage across the capacitor, we found this is V naught cosine omega t. So we had those already. And then both the current through the resistor is I, which is equal to I naught cosine omega t, and then we had current through the capacitor. We had I equals omega c voltage naught cosine omega t plus pi over 2. Okay, so putting all this together in a phasor diagram. So let's put this in a phasor diagram. So this is what we had for the phasor. So for the voltage across the resistor, we had VR. The current is the same direction. This is for the resistor. And then for the capacitor, we said the current was leading the voltage by 90 degrees. So this was the voltage in the capacitor, and the current was this way. This is the current in the resistor. So if we put them both together, this is what we shall have. So we have the voltage in the resistor this way, and the current is in the same direction. So if we flip the current through the capacitor so it lies in the same direction, then we shall have the voltage in the capacitor over here. And so the currents are all now in the same direction. So just looking at the voltages alone, we shall have the voltage in the resistor VR and the voltage in the capacitor V naught. Actually, let me put it as just V naught like I've been using all along. Okay, I'll use the V naught C, it's okay. So this gives us an effective E. So we can say this is the E naught. So E naught is equal to, or E naught squared is equal to VR squared plus V naught across the capacitor squared. So E naught squared is equal to current across the resistor and R squared plus current across the capacitor and the capacitive reactance XC. So we're going to have R squared plus XC squared, and we can take the current out and square it like that. This is the same current going through both resistor and capacitor, so I'll just call it I. So I is equal to IC. So the current in the resistor is equal to the current in the capacitor because they are in series, of course. So this is the current in the resistor. And any questions on this? So then if you take the square root of both sides, then you can say E naught equals I, and then you have the square root of R squared plus XC squared, that way. Therefore, the current in the circuit is given by E naught over the square root of R squared plus capacitive reactance squared. So that's the peak current I in the circuit. Okay, so from this we can find voltage drop across the resistor R. So we can say that the voltage across the resistor is equal to I times R. So we can say this is equal to E naught R divided by square root of R squared plus XC squared. So that's the voltage across the resistor. Don't forget that XC is equal to 1 over omega C. So keep that in mind. And then the voltage drop across, or the peak voltage. So the peak voltage drop across the capacitor is given by V across the capacitor, which is the current across the capacitor times the capacitive reactance XC. Okay, since the current across the capacitor is the same as the current across the resistor, we just write E naught XC over the square root of R squared plus XC squared. So that's the voltage across the capacitor. The voltage drop across the resistor is a peak voltage. So we just found the voltage drop. The voltage drop across the resistor, peak voltage. And if we want to find the instantaneous voltage, then we'll just take that I value and use it with the our value for current. Okay, so let's say, suppose we want the instantaneous current, I of t. We use I of t equals I cosine omega T like that. So we can use this for the resistor, and then so this is what we had for the capacitor. Okay, so let's look at filters. So this type of circuit is useful for building a filter. So we can have a type of filter called a high pass filter or a low pass filter. And so for the high pass filter, let's say we have this circuit like that. High pass just means the capacitor is up here, and then we have our resistor this way, and this is your output. So this is the resistor, and this is the capacitor. So this is a high pass filter. So this will allow you to transmit a frequency greater than frequencies where omega is greater than omega C, where omega C is called a crossover frequency. The crossover frequency occurs when voltage across the resistor is equal to voltage across the capacitor. So crossover frequency equation VR is equal to VC. So we can find omega C by setting the two voltages equal. VR equals VC, where VR is equal to E naught R over the square root of R squared plus XC squared, if you recall. And this should be equal to E naught XC divided by square root of R squared plus XC squared. So we can cancel a few terms to arrive at R equals XC. So we can say R equals 1 over omega C, like that. Therefore, omega C, which is a crossover frequency, so omega is equal to 1 over RC, and this is the crossover frequency. And so with that in mind, we can also build a low-pass filter. So for the low-pass filter, again, we have our circuit like that. This time we put the resistor up here and the capacitor this way, and your output is this over here. So this is C, and that is R. Okay, so this will pass frequencies less than the crossover frequency, and it will certainly block frequencies greater than the crossover frequency. Okay, all right, I think we should stop here and then continue on Thursday with RLC circuits.